I'm Sarah, and I love right triangles. And I've had some questions about Minnesota 2022 benchmark 9.3.66.6 and wondering why the phrase completing the square is in this geometric benchmark. And so I wanted to talk a little bit about the part in yellow comparing equations of circles, Pythagorean theorem, and the distance formula, and then talk about how that's connected to completing the square. Ultimately, this is a connection between algebra and geometry, and we want to see those things as intertwined. And so let me talk a little bit about this, but let me go back to eighth grade first, where students first experienced the Pythagorean theorem and the distance formula. You can see in benchmark 8.2.3.3, which precedes this in the 2022 standards, that students are using the Pythagorean theorem to find the distance between any two points on a coordinate system. Why do I love the Pythagorean theorem? Because I don't even think you need to know the distance formula. I think you can take any 2 points and draw on a triangle and think about the vertical change and compare it to the horizontal change. And you can find the slope of a line or the distance between the line. And you can square those things and do a lot of things with that. So let's talk about this ninth grade benchmark where students are being asked to compare and contrast and see how they're related. The Pythagorean theorem, which I love, here's a pretty simple right triangle with side lengths that are Pythagorean triple 3. The legs are 3 and 4, and the hypotenuse has a length of 5. Students could square 3 and square 4 and say that's a hypotenuse squared, and they could calculate and find that it has a length of 5. They also could do the same thing as put this same triangle on a coordinate grid and think about the length of that hypotenuse. Think about the coordinates of the two endpoints at 0, 0, and 3, 4, and ask themselves, what is the length of the hypotenuse? And they could develop and construct from the Pythagorean theorem the distance formula and see a relationship between the Pythagorean theorem and the distance formula. They're the same thing. They're just, the distance formula is just using the Pythagorean theorem on a coordinate grid. And then we could take that same triangle and translate it to another part of the graph. It doesn't have to be translated, but in this case I did translate it. And we could see this triangle this time as taking and considering the coordinate point -2, -2, the center of that circle, and thinking about the distance from -2, -2 to the point 1, 2 on the outside of that circle as a radius with a length of 5. And we could write the equation of this circle by using that center point where we use the letters HK, and we could write the equation of that circle using the circle formula. Again, if you take a look at the elements of the circle formula, it looks a lot like my favorite, the Pythagorean theorem. You see a distance squared and another distance squared, and then that's equivalent to the radius squared, and every point on the circle would follow that. And when students see the coordinates of that center point HK and see what the radius is, writing the equation is relatively easy for them. They could simplify this. X minus -2 is the same thing as x plus 2 quantity squared, and they could do the same thing with y. But if they're given the equation of a circle, and this is a valid equation of a circle, and they're asked to identify the center or the radius of the circle, they're going to struggle. So part of this benchmark is supporting students in transforming that equation of circle on the top, the one equivalent to 17, and transforming it into the one that you see on the bottom, which is equivalent to the one at the top, where it's easy to identify H and K and the radius in the one that's in the bottom. So how do students translate this? Well, there's another high school benchmark that as your school is putting these benchmarks into courses would hopefully precede the one that I was just showing you, that you would put this in a course or at a time in the course that precedes this one, and that lots of students would have reasoned abstractly with quadratics and developed procedures to convert from one type of quadratic to another one. And so we're hoping students have seen different forms of quadratic relationships, equations, and that they become really proficient at transforming from one to another. In this case, one that's going to be helpful for the benchmark we're talking about is transforming from standard form to vertex form, because one of the methods of getting there is completing the square. And you do that with quadratics. That allows you to find the coordinates of the vertex really easily. And hopefully, when they're doing this in their algebra course, they're doing it conceptually rich by seeing this phrase, completing the square, by seeing an actual physical square and completing that perfect square and doing some things with that. So let me give you an example. In order for students to do this, they need to be able to visualize in their head the elements of the equation and look at the quadratic expression x squared plus 6x plus 5, see the parts of it, and talk about if I wanted to create a square out of this, I would have to split up my x's evenly so the side lengths of that square are the same. I'd put all my 5 units there, but have I completed the square? No. I do know the side lengths would be x plus 3, but it's not a completed square. So to complete the square and to get x plus 3 squared complete, I would need 4 more units to do that. So my original one is x plus 6x plus 5 is the quantity of x plus 3 squared minus 4 additional units. And so students would have lots of experiences completing the square and doing that. So when they got to transforming equations of circles into the formula for a circle so that it makes it easy to identify the center HK and the length of the radius, they would look at the equation at the top, equation of a circle, and they would say, wow, I gotta separate out my variables, my x variables and my y variables, and for each of them, I need to create a square. By the way, I'll link to it in the description below, but I used Polypad to create these visuals. And so I created squares for each of these. I had an x squared and 4 x's, and I had a y squared and 4 y's. And I created each of those things, and I thought about what would I have to add to this to complete the square. And each of them I'd had to add 4 more units. And so if I add 4 more units to these to create squares, I better keep this equation balanced. So on the right side, I need to add 2 sets of 4s to that side. And then I can look at the lengths of the sides of the squares. In the first squared, it's x plus 2 times the quantity of x plus 2. In the second square, y plus 2 times the quantity of y plus 2. And 17 plus 4 is 25. And then I could simplify that to be an equation of a circle where it's much easier to identify h and k and the radius and find and identify important features of circles that would be useful. So hopefully your students are going to have lots of experience connecting the Pythagorean theorem to the distance formula to the equation of a circle, and one of the tools they use to transform equations will be completing the square.